Hi everyone, and thanks for joining for the latest ESCoE webinar. I'm Stuart McIntyre, a Professor of Economics at the University of Strathclyde and also a member of the ESCoE leadership. And it's my pleasure to chair this seminar this afternoon. We have presenting today Juan Reyes from King's College London, who's going to talk to us about his work on the macroeconomic effects of AI uncertainty. Juan will present for about 40 minutes before we turn over to Greg Thwaites from the Resolution Foundation, who's going to provide a discussion of Juan's work, and then we'll open to questions from the broader audience. If I could ask that if you have questions as we're going through the session, if you could add them to the Q&A function, then what we'll do is we'll curate those questions towards the end and invite you in to ask your question of Juan later on. So with that out of the way, let me now hand to Juan, who's going to talk to us about his research.
All right. Thanks for that, Stuart. So, all right. Good day, everyone. So, first of all, I want to thank ESCoE for the opportunity to present my research today, and I also want to thank everyone who took the time to attend this webinar. All right. So today, as Stuart mentioned, I'll be presenting my research titled "The Macroeconomic Effects of AI Uncertainty." And as the title suggests, I'm focusing on the second moment effects of AI, or again, the uncertainty surrounding it, rather than the AI's direct impact on the economy. All right. So let me begin um, by explaining my motivation for conducting this research. So as we speak, the development and adoption of artificial intelligence are expanding rapidly across firms and institutions worldwide. And for many countries, AI is now an integral part of their economic objectives and national strategies. Here in the UK, for example, the government emphasized that their commitment to adopt and use AI to boost growth and productivity. And this shows that AI is no longer just a technological trend, but rather it's essential part of the economic policy. Given this reality, the natural question to ask right now is what will be the impact of AI in the economy? So if we ask the IMF, Goldman Sachs, and McKinsey Global Institute, they will answer that AI will deliver substantial economic gains. For instance, IMF estimates that AI could increase global GDP by approximately 4% under a high productivity scenario. But if we ask Nobel laureate Darren Acemoglu, he will probably say that the contribution of AI will be small compared to the hype about it. Why? Because we also need to consider the challenges of adopting AI. And these opposing views about AI highlight the core issue that there is a fundamental uncertainty about AI development and adoption in the economy. And these opposing views are not limited only to those experts. The general public, like us, also holds mixed perceptions about AI. On one hand, we are very optimistic. On the other hand, we're also pessimistic about its implication. Like what most of us are asking right now, whether AI will replace us in our jobs. And the reality is, we still don't know, right? We still don't know how strong or how fast AI's effect will be. Because again, as we speak, AI is still evolving. And that lack of clarity itself creates uncertainty. And this uncertainty about AI is precisely what motivates me in conducting the study. So, prior research shows that when uncertainty rises, economic agents tend to hold back on their decisions. So, a well known work by Nick Bloom in 2009, for instance, shows that uncertainty can slow down the entire economy. And this raises an important question. Does AI-related uncertainty propagate through the economy in the same way as other sources of uncertainty? Yet, despite AI's growing economic importance, the literature has yet to examine second moment effects. Specifically, we lack understanding of how uncertainty about AI adoption and development propagates through the economy. And um, this is why the uncertainty dimension of AI also deserves our attention. As the IMF's chief statistician Bert Cross has said, and I quote, to truly understand AI's implication, we need to measure its impact across multiple dimensions. And that includes the uncertainty that it potentially brings to the economy. But now, how can we measure? The first question is how can we measure uncertainty about AI? Specifically, how do we capture perceptions of AI's influence on economic condition and future developments? So this brings me to one of the main contributions of this paper, where I developed the AI uncertainty or AIU index constructed from news articles. So this is actually inspired by the well-established approach of Baker, Bloom, and Davis in 2016 when they created the Economic Policy Uncertainty or EPU index. So uh, again, sorry, before I dive into the technical details of this research, let me just outline some key results. So first, the AIU index captures significant AI developments, such as the breakthroughs in generative AI models like the release of OpenAI's ChatGPT-4, DeepSeek R1 earlier this year, as well as some key policy initiatives about AI. So second, the AIU index shows low correlation with broader measures of uncertainty, suggesting that it captures a distinct dimension of uncertainty beyond what existing indices are already capturing. Third, focusing on the US economy, I find that AI uncertainty shocks generate contractionary effects on financial markets, labor market outcomes, and output. And lastly, labor market responses vary significantly across industries. So later in this discussion, we will see that the effects are heterogeneous, where some industries are hit harder than the others. All right. So before I uh, go to the key details of it, although I mentioned it earlier, let me just clarify again what AI uncertainty means in this context. Because I believe this is very important since I am introducing a new measurement of uncertainty. So by AI uncertainty here, I mean the perceived unpredictability of how AI will affect the economy. So this is a perception-based measure. So it reflects public discourse rather than the true or the objective uncertainty. So in here, high uncertainty indicates heightened debate, concern, or disagreement about AI's impact on the economy. So following Baker, Bloom, and Davis in this aspect, I interpret this as a useful proxy for periods of elevated AI-related economic uncertainty. Okay, so since we have already established the definition, let me just guide you on how I constructed the index. However, for the benefit of the time, I will just briefly outline the main steps. So, as mentioned, I follow Baker, Bloom, and Davis to capture perceived uncertainty. And to measure AI uncertainty here, I use news articles from top providers in the US, UK, and the Euro area obtained from Dow Jones Factiva. And then I filter these news articles and only retain those that collectively mention the words such as artificial intelligence, economy, and uncertainty, or their related keywords. So in this way, I only focus specifically on the moments where AI is explicitly discussed as a source of economic uncertainty. Then, to ensure the comparable coverage across news outlets over time, I apply several normalization procedure. So first, I scale each outlet by its total article count. So this prevents larger outlets, let's say Wall Street Journal or Reuters News, from dominating the index. Second, I standardize each series to comparable variance scale, so spikes across different outlets can be fairly compared to one another. Third, I renormalized to a common baseline period and combine them to a single monthly index. And then to validate the index, I review the articles, like each and every articles behind the major spikes, and link them to significant AI events that plausibly raised economic uncertainty. So this in this I follow Romer and Romer's approach in their paper in 2010, wherein they identify key events in order to identify fiscal shocks. And then finally, I test AIU's or AIU index distinctiveness through correlations and regressions, which confirm low correlation with broader uncertainty measures like the EPU index of Baker Bloom Davis, the Real Economic Uncertainty Index by Jurado and his co-authors, S&P 500's Volatility Index, and as well as Nasdaq 100 Volatility Index. So just a quick word on the justification of this approach and scope. So here, I use a dictionary-based approach to ensure that the index is transparent and directly comparable with existing uncertainty indices. Um, while alternative method, of course, such as sentiment analysis, topic modeling exist, I treat them as a robustness checks rather than replacement. So I'm keeping the baseline here clear and again comparable for macroeconomic analysis. Um, for this study, I construct a global index because AI is inherently a global phenomenon, mainly because the same AI is used worldwide. So again, same AI tools operate across industries, firms, and countries worldwide. So when capabilities change, such as when, let's say, OpenAI introduces a new model for ChatGPT, media narratives spread rapidly across borders, making AI uncertainty fundamentally non-local. So here is the AIU index from January 2016 to April 2025. So um, as we can see here, there are notable jumps exhibit around recent AI-related events. So, for example, there are spikes following GPT-4 release and when DeepSeek R1 was released earlier this year. And by looking at the movement of the index, one fascinating thing here is that when ChatGPT was introduced in November 2022, AI uncertainty remained relatively low. But over time, uncertainty increased as I think the public became more aware of what these generative AI models could actually do. And here we can see the AIU index plotted alongside with other uncertainty measures. So indicating that heightened perceived uncertainty about AI is not captured by these existing indices. Notice how AIU index remains flat, until around 2023, then exhibits distinct spikes that don't align with other indices, particularly the sharp spikes in 2023 to 2024 and the recent spike in 2025. Um, in contrast, here, measures like EPU, the REU, VIX, and the NASDAQ Volatility Index show a major synchronized spike, let's say in 2020 during the COVID-19 pandemic, while the AIU barely moved during that time. So this confirms that they're capturing different sources of uncertainty. And this virtual divergence is supported by the correlation and the regression numbers, where AIU index only correlates weekly with this traditional measures, typically around 0.2, ranging from negative to positive. All right. So now we move on to the second part of this research, where I examine the macroeconomic impact of AI uncertainty. So here, I use two complementary approaches. So I use a structural VAR to examine the aggregate level effects and local projections to assess industry level responses. So for the local projections, I follow what Diego Kansig did in his paper, using the identified shock from the structural VAR. So I extracted that shock and put that in a local projection setup. So it's like here. So epsilon here, epsilon t AI is the shock from the structural VAR, and I extract it and put that in a local projection setup. Okay. And to identify AI uncertainty shock, I use two alternative identification strategies and structural VAR. So the first is I use the traditional recursive identification, where I assume that AI contemporaneously influences all macroeconomic variables inside the VAR, but not other way around. And the other one, to relax this assumption of timing restriction, I also identified the shock using instrumental variables. Specifically, I used the tail realization of the AIU index and the residual from the AIU index, and from the AI economic news index, which I discuss further in the next slides. All right. So let me just um, uh, take a brief moment to explain SVAR IV and the instruments that I use, so we are all in the same page in here. So SVAR IV, also known as proxy SVAR, and as the name suggests, it uses external instruments to identify structural shocks. So so extending the instrumental variable regression that we know, but we put that in a VAR setting. So therefore, the instrument must also satisfy two conditions. So it should be correlated with the structural shock of interest. So in this case, AI uncertainty shock, but it should also be orthogonal with other structural shocks in the system. So essentially, this approach does not depend on the ordering assumption like the recursive identification, making it more robust alternative identification strategy. And I verify these conditions, the two conditions, through the covariance between the instrument that I propose and the reduced form residuals, reduced form from the VAR model. All right. So the first instrument that I use to identify AI uncertainty shock is the tail realization of the AIU index. So basically, this is a dummy variable it's equal to 1 when the AIU exceeds its 95th quantile, or a 0 otherwise. So the logic behind here is that while endogenous responses to economic conditions may contaminate the AIU index, the extreme spikes in the AIU, as presented earlier, are more driven by exogenous AI events, such as major breakthroughs or regulatory announcements. So, this tail approach helps isolate through exogenous variation in AI uncertainty. Okay, so the second instrument that I use is the regression residual from regressing the AIU index on another index that I created, which is the AI Economic News Index. So basically, the AI Economic News Index is constructed similarly to AIU, but without the uncertainty keyword, sorry, without the uncertainty keyword uh, in the filtering process. So, therefore, the the AI Economic News Index captures the AI news coverage in general, not specifically uncertainty about AI. So, what's the reason behind this? I use this approach because uncertainty shocks are often confounded by first moment shocks, such as news and total productivity shocks. So studies by my supervisor, Michele Piffer, and his co-author, as well as Danilo Cascal de Garcia and Ana Galvao, have documented this confounding issue. And by removing the component of AI uncertainty that correlates with general AI news, I isolate its pure uncertainty dimension, uh, addressing this potential contamination. So, all right. So, turning into the empirical design. So again, I focus on the U.S. economy at first in this preliminary paper, with industries classified under the North American Industry Classification System. So for the aggregate analysis, I use a six variable structural VAR, and for the industry level analysis, I used a local projection focusing specifically on labor market outcomes. And the sample period spans from January 2016 to April 2025, because this is the subject to the availability of the AIU index. And then finally, I just apply standard robustness checks in conducting structural VAR, including appropriate lag selection and COVID-19 adjustments to ensure the reliability of my results. So before turning into the result of the structural VAR, which is the impulse responses, let me first present the instrument's validity. So the instrument that I discussed earlier. So the diagnostics here confirm that there's no weak instrument problem. So all F statistics, as we can see here, exceeds stock in Yogo's threshold of 10, indicating that the two instruments that I proposed earlier are valid. Okay, so there's no more than 10 F statistics in the other equations aside from the AI uncertainty shock that I want to identify. Okay, so here are the impulse responses from both identification strategies, recursive identification and structural VAR IV, using the tail realization instrument. So interestingly, the results reveal mixed effects on after AI uncertainty shock. So most notably here, there's an expansionary effect on S&P 500, which seems counterintuitive, right? Since most of the time when there's heightened uncertainty, equity prices contracts. So later, in the other IV, I'm gonna present that this is not the case. Um, Turning into the labor markets, hours work declined significantly following the AI uncertainty shock. And in contrast, the responses of wages, employment, and industrial production are more muted. So now, when I use the second instrument, the residual of the AIU index and the AI economic news index, so the impulse responses tell a different story. So once I orthogonalize AI uncertainty from general AI news, the shock generates broad-based contractionary effects across all macroeconomic variables in the system. So these are the red lines here with the red band. So these are the impulse responses from the structural VAR using instrument, uh, using the residual instrument from AIU and AI Economic News Index. And we can also see here um, that most of these effects are transitory, where the variables promptly revert after the shock. Okay, it contracts, but it promptly revert to the baseline in the short run. So, however, in here, the most interesting part is the wages. So the wage response shows notable persistence. So the contractionary effect on wages builds up over time, and it remains below throughout the entire horizon. So I think this is a pattern consistent with the sticky wage in the labor market. So yeah, okay. So the forecast variance decomposition backs up what the impulse responses are showing us. And as we can see here, AI uncertainty shocks explain a large number of variance in S&P 500, hours work, and industrial production immediately after the AI uncertainty shock. So as we can see here, let's say S&P 500 on impact, the error variance is 10.9. And after that, it decreases, let's say at the 36-month horizon at 8.51. Okay. And for the wage here, the story also backs up the impulse responses. So at impact, the AI uncertainty shock only explains 2.6% of wage. So the contribution of AI uncertainty grows slowly and ultimately dominates at the longer horizon. Again, what I can observe here is that this persistent pattern really highlights how sticky wages are in response to uncertainty. So what happens when we zoom into individual industries? So the local projections reveal patterns that somewhat echo the aggregate results. So following the AI uncertainty shock, most industries show contractionary wage responses. Some are, as we can see here, some are sharp, while others are more muted. But um, but here's the interesting part. We can see here that the financial activities or the financial industries diverge from this pattern. It can be seen here that wage in the finance industries actually increased following an AI uncertainty shock, following in opposite direction from nearly every every sector that I include here. So later, I'll offer a potential explanation for this puzzling result. For hours work, it tells similar story from the aggregate result. So following AI uncertainty shock, they contract, but only in a very short amount of time. So as we see here, leisure and hospitality, for instance, illustrates this pattern nicely, wherein it declined approximately around 0.3% on impact, Then it returned to baseline within 2 months following the shock. And other and most other industries here follow the same transitory pattern, though the effects here are generally smaller than what the aggregate impulse response suggests. Okay, so in the case of employment, we can see here that the aggregate pattern emerged across industries, wherein contractionary responses are the norm after an AI uncertainty shock. The most significant contraction here is in leisure and hospitality, where employment falls approximately around 2% following the shock. However, since the confidence bands here are quite wide, I can't be too definitive about this result. So it's quite statistically insignificant. All right. So let me return to that puzzling wage story, right? So why do aggregate? So okay, so in structural VAR, we know that it's contractionary, and in industry level result, it looks different, specifically in financial industries. Remember again that aggregate impulse response shows wage respond negatively after an AI uncertainty shock, but the industry breakdown reveals something more nuanced. Only here earlier, only the financial industries show wage increase while other sectors see wage declines. So this creates a puzzle because VARs and local projections should theoretically give us the same answer. So here I have two hypotheses why this is the case. So one of my hypotheses centers on the composition effects. So if even if finance wage increases, finance may represent only a small share of the total employment. So larger sectors showing contractions uh, may be dominating the aggregate impulse response. So my intuition here is quite simple, so that small industries with large gains cannot overweigh big industries with modest declines. And to formalize this hypothesis, I calculate the employment shares per industries, wherein I also verified this using BLS, like the Bureau of Labor Statistics, employment by industry per sector. And alternatively, financial industries may genuinely, maybe it's really benefiting from AI uncertainty due to their unique exposure to AI, creating a sector-specific wage premium that don't translate to economy-wide effects. And to explore this, I turn to the recent work of Edward Fulton and his co-authors. They're from Princeton and NYU, who developed an index measuring how different occupations, industries, and geographic areas are exposed to AI. And the index quantifies the overlap between an occupation's required abilities and AI's capability. So here, a positive value greater than zero indicates a high exposure to AI, while a negative value indicates low exposure. So here's where the story comes together. And I have to say, this is my favorite chart in the whole paper so far, since it's one of my latest result, and it tells really the story out of it. So this plot shows AI exposure on the x-axis and wage responses from the local projections at horizon 6 months after the shock on the y-axis. So let me start with the bubble sizes here. Those are employment. These are employment shares. See how finance is actually pretty small, right? So it's like blue, a blue area here. So its employment share is really small compared to the big bubbles, like let's say trade and transportation and utilities, or professional services. That's so this is going to matter in a moment. Now look at the x-axis here at AI exposure. Finance is out way 1.5%. So it's really high exposed to AI based on uh, Felton and his co-authors measurement. Meanwhile, manufacturing is negative, meaning its work doesn't overlap much with that much of AI can do. Now, here's the interesting part. So there's really a strong relationship between the wage responses after an uncertainty shock, after an AI uncertainty shock, and AI exposure. So it's 0.79, and it's statistically significant at 0.02. So what this means in simple terms is that industries more exposed to AI consistently see wage increases when AI uncertainty hits, while less exposed industries see wage decline. So financial activities makes the perfect point in here. Highly exposed, biggest gain, 0.05%. Then we've got manufacturing and leisure and hospitality down here, low exposure, wage dropping. So here how this solves the puzzle earlier. Yes, AI exposed industries like finance do get somehow wage premium when AI uncertainty rises, but finance is too small to move the needle at the aggregate level. So it is the big employment heavy sectors with lower AI exposure that pull the aggregate, what we can see earlier, the impulse responses in the structural VAR. So let me um, wrap up with my conclusions. So first, AIU index provide a novel and timely measure of AI-related uncertainty that captures fundamentally different from what existing indices already measures. Second, AI uncertainty is an emerging as a distinct driver of business cycle. It generates contractionary effects on output, employment, and hours worked, with particularly persistent impacts on wages. Third, industry level results reveal that AI uncertainty doesn't diffuse evenly through the economy. High AI exposures, industries like finance, see wage premiums, while low exposure sectors contract. And the aggregate estimates from the structural VAR mask these important sectoral differences. And here are just my next steps to further improve this paper. So first up is to refine the index. Second is to I'm planning to dig deeper into the macroeconomic impacts of AI uncertainty, looking at the business decision, consumption patterns, maybe, and productivity effects beyond what we have seen earlier in labor markets. Third, I want to test whether AI uncertainty operates through traditional real options channel. Most of the people focused on uncertainty raised that people are waiting and before doing something, or if AI uncertainty triggers distinct precautionary and wait and see behavior that is different from that. And finally, I'm currently conducting robustness checks, as mentioned earlier, using alternative construction methods, particularly sentiment analysis and topic modeling, just to validate if to validate the dictionary approach uh, that I did. So I think that's it for me. So thank you very much for listening. Looking forward to the questions.
Thank you, Juan. If we could just move straight to Greg. If Juan, if you stop sharing your screen and Greg starts. Thanks, Greg.
Can you hear me okay?
We can.
Super. Yes, I've had terrible IT problems this morning. At one point, I had 3 devices on in this room, all with their cameras onto me. And so, if you saw 3 pictures of me from an angle, I'm not. Or at least I don't think I'm a narcissist. I'm just someone who can't work a computer. But I think we're okay. All right. So, thank you very much indeed for the invitation and the opportunity to read this paper. Here's a nice chart I think that we could be using to motivate this. So basically, AI uncertainty is very large. Like a reasonable modal case is that it boosts trend growth a tiny bit, but is worthwhile. But on the upside, none of us ever have to work again, and on the downside, we're all going to die. So I think yes, I think the AI uncertainty is very large indeed. So what this paper does is a useful contribution to what we know on this. So Juan identifies news-based AI uncertainty shocks in a kind of Baker, Bloom and Davis kind of style. He uses them in an SVAR and in an LPM, and then measures impact on real financial and industry level variables. And what I liked about it, of course, was the choice of topic. I think that's the most important thing that you can do, get the topic right. I think the use of text-based methods is appropriate, and as far as I can tell, it's well executed. I think the thing I love the most actually is this attempt to separate hype or coverage from uncertainty, and this is something that I've struggled with working with uncertainty. Like for example, when the peripheral European debt crisis happened in 2009, 2010, the uncertainty about like what was going to happen to Greece shot up. But if all that had happened was that there was a mean preserving spread of outcomes for Greece, then of course the probability of something really amazing happening to Greece would have gone up as well. But basically all that happened was uncertainty increased, but the first moment went down. So it was like, how bad is it going to be? And that's why that plagues everything in this literature, right? Like normally when there's higher uncertainty, there's usually some kind of change in the first moment, usually a negative change in the first moment. AI is probably different, isn't it? And so that's why it's so important and welcome that Juan has done this. I think local projection models are the right approach, especially when you're looking at industry level measures. Very clearly explained what he's doing in the paper, and I like that he bootstrapped the confidence intervals. So I've just got a few suggestions and comments about the analysis with this very constructive and positive spirit in mind. So the first one would be looking at the data. The data isn't like the best behaved data, and that's of course no fault of Juan's. That's because he's dealing with a very new topic, and so basically all of the identification in the estimates is coming from the end of the sample, isn't it? You have like a not very wiggly line, and then a very wiggly line at the end of it. Then you've got the pandemic halfway through the sample. And I suppose one question I have, and this is like a genuine question, will the wild bootstrap give us the right confidence intervals when the data looks like this, when there's massively heteroscedastic shocks? And maybe the answer is yes, but I think it would be good for everyone if one can convince us of that. Because if, for example, you were to just, let's say, take the first bit of the sample, like there's nothing going on there, right? So I think the wild bootstrap deals with this because you're basically multiplying the fitted residuals by some time varying number. So I think it will work, but I'm not convinced, and I would like to be convinced of that. And if I was like a referee in a journal, I'd want to be convinced of that. The second question I have is that, like, while in principle I think it's very good to try and distinguish between coverage and hype or uncertainty, it's very difficult, isn't it? And if I understand correctly, the pure uncertainty index is like the residuals of projecting the red line on the blue line here, right? And you can see that they're extremely collinear, and this is the result. So on the one hand, like, I think it's amazing that we still get something having done this. but I think that maybe a little bit more explanation about how that works and how much we can trust it would be good. But this is not to be critical. This is to say that Juan's done the right thing by trying to distinguish between the red and the blue line, even though they're nearly the same, and we still get something. So I think that's amazing and worthy of further examination. The main suggestion I had, I think Juan's already done. Now, I think that might be because he said this was work that was just hot off the press. But basically, to try and parameterize exposure to AI. So you have all of these different industry level local projections here, and we know that they're exposed to AI in a different sense. And you can interact this pure uncertainty shock with an uncertainty measure. So one way of doing it is just estimating all the regressions separately and then plotting the coefficients, which I think is what I saw just now. I don't think that was in the version of the paper that I saw.
Yeah.
The other way to do it is to do an interaction term. So you essentially, if you like, you're kind of estimating that line of best fit between the parameters in one go. So I would suggest that. The other main suggestion I would have for Juan is to exploit higher frequency data and identification. So the news is like daily or hourly potentially, right? There are some data which are also very high frequency, higher frequency than things like industrial production. And an example would be industry level share prices, rather than looking at the whole S&P. People have had now some success using job posting data, which is very high frequency and granular. Now, of course, LinkedIn or Indeed is not a representative sample of the economy, but it's pretty good. And so I recommend that that Juan tries that, because I think that the problems that we've got, which is basically everything's happening in the last few years,